Hi folks, and welcome back to my basement. I'm here today to record a lecture to be given in place of class on Thursday, talking about the idea of dependency being addressed in multi-level models, as well as a little bit about the under the hood aspects of estimation. So first, a conceptual description about dependency. The idea is that the way that these multi-level models address dependency is by distinguishing reasons for correlation of observations from the same cluster and articulating those reasons into new variance components. So once upon a time, there was an outcome and it had all of its variability in one pile, so to speak. The first thing that we do is distinguish the part of that outcome that is within clusters, people from the same sampling unit, versus variation in the mean response across clusters. The idea that some clusters are higher on the outcome on average than others. Well, each of these sources of variability we can then explain by adding fixed effects, such as the within cluster version of a level 1 predictor. So the idea of having relatively more of predictor X than other people in your unit. Also, being from a cluster that has relatively more of X than other clusters on average. So the cluster mean of a level 1 predictor can help reduce level 2 intercept variance that represents between cluster differences. The within cluster deviation can help to explain person to person within cluster variation. But if we wanted to allow differences between clusters in the effect of this within cluster predictor, so differences between level 2 clusters in the slope of a level 1 person predictor, that actually comes out of residual. So once we allow a slope, we have repartitioned the variability that we were calling within cluster into a separate component that is between. So when all is said and done, we end up with this configuration right here. We have two different kinds of cluster dependency due to mean differences via the intercept, due to differences in the effect of a person predictor as a random slope at level 2, and then we also have still some remaining within cluster person-to-person variation. And as you might note from the little bit of green here, it's possible that this also contains unmodeled cluster differences in the slopes of other person predictors, in which case we could pull those out, create another green circle here, and then we would have three ways that clusters differ from each other. So the idea is that dependency is addressed by distinguishing reasons for correlation and pulling them out of the residual. The end goal is that the residuals then should behave like they would in any standard regression model. They should be independent with constant variance and normally distributed in this case. The normal and constant variance part we can change by switching to generalized models, but they should be independent because all the reasons for cluster dependency should be captured by the level 2 model, and those reasons get to have covariances as well. So that's the conceptual description of how this works. Now here's a little bit more on the math side. Here's some predictors too, forgot about that. So remaining within cluster residual variance can be captured by other predictors. Other main effects of level 2 predictors can capture intercept variance, and cross-level interactions, so a level 2 predictor interacting with the level 1 predictor the random slope is 4, can explain level 2 slope differences. So in this case, it's a random slope for within cluster X, so the within cluster X predictor can interact with a cluster mean predictor in this case, or any other level 2 predictor to account for random slope variance. Okay, so up to this point, the way that I presented these models is using what are known as scalar equations rather than matrices. However, looking at the model from this perspective doesn't readily convey how the model predicts the variability in an outcome and also the covariability across units in the outcome. For that, we need to have matrices. So I'm going to use this relatively simple model relative to the rest of these slides in this lecture 4 anyway. By the way, I'm on slide 43 of lecture 4, probably should have said that already. This model has a fixed effect only, fixed slope of a level 1 predictor, a fixed slope of a level 2 predictor, a random intercept, and a level 1 residual. So in addition to the fixed intercept, this is the model. So you can see more directly what it contains in its composite form. Another way of writing the same model is to say y is equal to a matrix that is cluster specific, that has predictors in it, fixed effects, random effects, and the predictors that go with them, and residuals. So by the way, this terminology is also used in SAS mixed output, which is where I got it from. And this should be a YPC in front of this thing here. I'll fix that after I'm done recording. So putting it together, this model right here would look like this in matrix form. So note which of these matrices have C subscripts and which don't. The ones that do are cluster specific. So Y is the vector of outcomes from all the people who live in the same cluster. X is a matrix of predictors to be given fixed slopes. So this is sometimes called a design matrix. That comes from design of experiments or ANOVA language. And right now we have one column for the intercept, so that's the column of ones here. We have a second column for the level 2 predictor, so cluster mean X, and a third column for the within cluster predictor, which is the level 1 predictor in this example. So that's the contents of X. Gamma then, I've used it as a matrix version here, so you can't really tell, but it's bold and not italic to try and make it look a little bit different. This contains the actual fixed effects that are to be multiplied by these predictors. Then we end up with the random part of the model, where Z is a cluster-specific matrix of predictor values to be given random effects. Well, in this model, only the intercept is random, so all we have here is a column of ones that would go with the intercept, and then U is a matrix that contains the cluster-specific random intercepts. E then is a matrix of residuals, one for each person within this cluster. So if you do the matrix multiplication here, it works out to look very similar to what the scalar equation looks like. So we have the fixed effects here multiplying their, their predictors. We have my random intercept here that's multiplying a 1, so that part goes away, and then the e's. And then when all is said and done, it looks like this. Okay. Now, how do we get to the model implied variance of y and covariance of the y values from people from the same cluster? Well, that is the result of forming what is known as a G matrix, which is a matrix that holds the random effect variances and covariances, and it gets wrapped around it, pre and post multiplied, by Z, which is still the matrix that has the values of the predictors that have been given random effects, and Z transpose is the same thing on its side. So we have in this model, because it only has a random intercept, we only have one number that goes in the G matrix, so G is 1 by 1. We have the ones that represent the intercept for each person within the cluster here. And we have the same matrix post multiplied here, added together then to get the R matrix, which is the residuals. And we are assuming that the residual variance is the same across persons and across clusters. So if you do the math through this, the V matrix looks like this. And this style of matrix has a particular name. It's called compound symmetry. And on the diagonal, what it's saying is that the total variability for any person is a combination of what cluster they come from, so variance across clusters in the intercept, plus themselves, the E for that person, the E across people. So the total variability is the same across all people, and covariance between people from the same cluster is given only by the random intercept variance. So another way of saying this is that this style of V matrix, again compound symmetry, assumes that correlation across people from the same cluster is due only to cluster mean differences, only to the random intercept. So people are conditionally independent, meaning after we control for which cluster they're from via this U0 variance here, then they're independent. So R is the idea of we've figured out all the reasons why some people would be more related if they're from the same cluster, and those reasons are supposed to be over here in what is called the G matrix. If we add a random slope, then what we are doing is expanding the reasons why some people from the same cluster, would be more related than people from different clusters. So if I add a random slope to the model, so for instance, I give a random slope to the effect of within cluster X, this U1 term right here, or right here, what that means is that we are saying each cluster gets their own specific effect of within cluster X. So gamma 1O becomes what happens on average. U1 is how far off your cluster slope is from that average slope. So now there are two different U's in the model, an intercept and a random slope. That translates into two different reasons for cluster dependency and two different patterns of relationship among the people from the same cluster. So the matrix equation looks exactly the same, and this is one of the reasons, quite frankly, I don't use it that much, because when you stare at this condensed version, you can't tell what's in the model. It's really untransparent. So I like writing things out to be explicit and as transparent as possible, because this stuff is already challenging enough. So I had to shrink the font to fit everything in here, but it's the same idea as before. The X matrix, again, holds the predictor values that are going to be given fixed effects. Gamma holds the fixed effects. Z holds the predictor values that are going to be given random effects. And now we have two, an intercept and then the predictor that the random slope is for. So now these are both contained within cluster X's in both places. Note that cluster mean X is not in Z because it's not being given a random slope. So Z cannot have more stuff in it than X, but X can have more stuff in it than Z. You can have fixed effects without the corresponding random effects, but you cannot have random effects without the corresponding fixed effects. Things will go badly. U then has two elements in it now, the intercept for each cluster and the slope for each cluster, and then a person-specific residual. So then when you work out the math, it looks a lot like the equation in this form right up here. Now, what happens in terms of the model implied variance and covariance is a lot more complicated. So I have the pieces up here. Again, Z holds the predictors that are being given random effects for each cluster. G holds the random effect variances and covariances that are in common across clusters. So note that G does not have a C subscript here. So we have a random intercept variance in spot 1, 1. We have a random slope variance in spot 2, 2. And we have the covariance between them in row 2, column 1, and also row 1, column 2. So it's a symmetric matrix. R looks the same as before because we're still saying the same thing, that people are conditionally independent, but now they're independent after two reasons are factored out. Cluster mean differences to be given by the intercept, which is now specific to the zero value of the slope that the random zero value of the predictor, that the random slope is for. So many words, my goodness. And lost my train of thought. Okay, yes, two reasons. This one and that one. There we go. So if you work out the math here and do the matrix multiplication and addition, what ends up happening on the diagonal of the V matrix is this complex function right here, where the total variance starts with the random intercept as before, the random intercept variance, and ends with the level 1 residual variance as before, but inside the middle are the new additions that are created when you add a random slope. So the variance at each specific level of within cluster X, it's conditional now because of the random slope, is a function of that predictor value squared times the random slope for the within cluster predictor. So that squared term right here, that's what creates a quadratic pattern of heterogeneity of variance along the predictor the random slope is for. It's a U shape. And added to that is also the covariance. So this function implies that there will be some point along within cluster X at which the variability is at a minimum, and it will increase in a U shape, from either side of that. So there is no longer a variance to be recovered by the model. The variance is predicted to change systematically with this pattern along the values of within cluster X. Likewise, the covariance between any two people from the same cluster, such as person A and person B, is a function of their specific values on the predictor the random slope is for. So the covariance is no longer just the level 2 random intercept variance as it was when we only had a random intercept. We have all this extra stuff thrown in here. So to say this more directly, the covariance between two people from the same cluster depends on their values of the predictor to be given a random slope. So that's where this quadratic variance pattern came from. And just as an aside, you'll note that I'm using the within cluster version of this predictor so that the quadratic pattern of variance along this predictor does not also get applied to the level 2 part of the predictor. If I had used a constant centered level 1 predictor, then this quadratic variance pattern would be assumed to hold equally across the cluster mean of this variable as the within cluster part. So that's the idea of a conflated or smushed random slope that we want to avoid by making sure that what gets this heterogeneity of variance is only the level 1 part of the predictor. That means we are saying there are cluster differences in the within cluster slope of my person predictor only. But that's not all. I've shown you what the V matrix would look like for one cluster. Here is what it would look like for two different clusters, each with 4 people in it. And this pattern of like stuff and then zeros on the off diagonal chunks here, these chunks, this is known as block diagonal. And what I've drawn the purple boxes around are the parts that apply to just one cluster or the other. So let's say that cluster 1 here has their intercept column. In Z, they have values of the predictor the random slope is for here. Cluster 2 has the same thing, but with different values for their random slope predictor. Each cluster shares the same variance components, so the random intercept variance, the random slope variance, both at level 2 here, and the covariance between them. And then we have Z tipped over on its side again to make it so that the results of this product can be added directly to R. And then within R, we have the same independent structure here, saying there's constant variance across people and no covariance because all the reasons for the covariance of people from the same cluster should be over here in the G matrix instead. And the reasons that we have these zeros and these off block elements is because clusters are supposed to be uncorrelated. So for instance, if this were a model of children in classrooms, but some of the classrooms came from the same school, that assumption of independent classrooms would probably be violated. Instead, we would need to add another level to the model that would introduce a correlation of classrooms from the same school. That would require adding something to these off-block elements that would allow certain clusters to be correlated and not those from different level 3 units. So that's what we'll be talking about as a 3-level model. Maybe by the end of the semester, we'll see how far we get. In this example, both clusters have the same within cluster sample size of 4, but it doesn't have to be that way. Let's say that one cluster only has 3 people instead. No biggie. V just stretches or shrinks to contain the right number of observations per cluster. So it doesn't have to be balanced or the same. So the end result of this here is what we have is between cluster differences in G, we have within cluster variation in R, and through the pre and post multiplication of a matrix that holds the values that go with the predictors the random effects are for, we combine it into this complex V pattern that gives us the overall predicted pattern of variance and covariance across people and clusters. So there's a lot of flexibility in what you can put in these elements. For instance, in R, in longitudinal data, sometimes we would put an additional correlation that would allow the residuals to be correlated over time above and beyond the random effects. In the context of cluster data, that wouldn't make as much sense, and so R is almost always going to be of this diagonal pattern with zeros, an identity matrix, or not identity, excuse me, diagonal matrix, I think we'll call it that. Okay, so now how do we get the answers that would go into all of these things? I want to give you a little bit of an overview of that. There are much better sources for this, I will tell you that much. Estimation is not my strong suit, but I'm going to try and give it the 3,000 foot view. So in terms of figuring out what our model parameters should be, We want to think about the fixed effects that belong in the model of the means separately from the random effects, their variances and covariances that belong in the model for the variance. So the key idea is that in the models we're talking about right now, general multi-level models, meaning with a residual that is supposed to be normal, fixed effects do not have to get solved for iteratively. They do not have to get found. They can be computed after the fact once we know what the parameters should be in the model for the variance. So every additional parameter, either a random effect variance or a covariance that you add in here, is going to increase the complexity of the estimation process because those all have to get solved for in an iterative basis. So I want to show you a little bit about that and how it works using the previous random slope model. So recall that we had a random intercept and a random slope. We had a level 1 predictor, a level 2 predictor, and a fixed intercept, as well as a level 1 residual variance. So there's basically 3 steps to the process of maximum likelihood. One is to figure out which estimates make the data the tallest, which are most likely. And then number 2 is to figure out the precision of those estimates. So how sure are we that they are actually the most likely, or is it just really a guess? Then we can determine indices of model fit, and we can compare those to determine whether or not we want to add things to the model or whether it would be okay to subtract things and go with the simpler model. In the current types of models we're talking about, all of this happens through the magic of the multivariate normal distribution, but just to illustrate, we'll start with univariate normal first. So here's this picture that I've stolen from Wikipedia a long time ago. This is a probability distribution function or density function, and this is our friend the normal distribution. Here's a formula that gives us the normal distribution. So if you know 2 things, in this case this is an empty model, so we have just a mean and a variance, the 2 parameters that you have to know for a univariate normal distribution. If I know the residual variance here in blue and I know what the fixed effects say the predicted mean should be, so in this case it literally is just the mean, then I put those things into this formula, come back, and no, there we go, and out pops a number. The number is the value on the y-axis here, so that's the likelihood of that particular observation given the distribution that you're working with. So for instance, if I'm at 0, then that likelihood is much taller if 0 is part of this blue distribution that has a mean of 0 and a very small variance than if it's part of the red distribution where the variance is extended, so that you're going to be less certain or less likely to have any one value the wider these things go. Likewise, if I'm from the blue distribution and my value of 0 is not very likely because the blue distribution has a mean of -2, so very few cases would be as far away as 0 is in this case. Okay, so key idea, given the model parameters, you can compute the height of the outcome. In our case, however, we don't just have one outcome. What we have is a multiple outcomes per cluster as the unit of analysis. So we would have to adapt this formula to be able to address multiple outcomes from the same cluster. So we go from the univariate normal distribution, which looks like this, rewritten slightly so that it looks a little bit more parallel, to multivariate normal. So the big changes, rather than having a single y per individual, now we have big Y for every individual from that cluster. Rather than having a single residual variance, as you would for a single level regression model, we have our friend V, as just introduced earlier in this lecture. V is the model implied variance covariance matrix that gets built from all the random effect variances and covariances along with the residual variance. So in this example, we have 4 parameters that we need to build V: random intercept variance, random slope variance, covariance between the 2, and level 1 residual variance. Then we go over here in this part, this same idea of residual here, so what you have minus what you were predicted to have by the model, that same idea is right here in matrix form, where we have x gamma instead of the predicted hat directly, but it's doing the same thing. There's our friend V replacing residual variance again, and then here's the residual. So this matrix T in this one here, that is basically squaring things. So whenever you see two matrices of the same kind next to each other and one's transposed, that's usually a squaring type operation. So in this model then, a couple things to point out. This bar thing around V, that is a symbol that means determinant. Determinant is a matrix, how do I say this? Matrix characteristic, maybe? It's something that you can compute, but it's very difficult to do so by hand, particularly for larger matrices. And what it essentially amounts to is the amount of information that is non-redundant in V. So it's sort of like trying to factor out covariance and figure out how much information is in there. And the big idea is that you cannot have that go to zero. Taking the inverse of V right here, let's see here, where is that? Right here, that one right here, is like dividing. So V cannot be 0 or negative. It has to be positive definite. So you may see error messages in your software that say things like not positive definite. That means something is broken in V. Probably it means that one of your random effect variances went to 0, or that the covariance between your random effects went to a boundary value for the implied correlation. So correlations are supposed to stay between -1 and 1. It's possible that the value of a covariance that it decided was most likely is out of bounds with respect to the correlation that it implies. So things to watch out for here. Basically, V is what will break the system if some of your variance components go to 0 or the correlations among them go out of bounds. So once you have V, though, we can figure out how tall the observations from the same cluster are. So we are multiplying across observations from the same cluster, or summing across clusters in this case, and again pops out a number. So usually we're working with log likelihood because it makes the math easier to work with. And the name of the process is to try out different values for what the random effect variances, covariances, and residual variance are that make up V until you get to the highest possible set of log likelihoods. So you try on different values, compute a result, try on something else. Does it make it taller? Okay, we're heading in the right direction. Does it make it smaller? No, we're not. Okay. In practice, there are very sophisticated ways to figure this out based on calculus. That's about as much as I can tell you with any level of confidence. But I do know that as you're trying to figure out changes in the relative height of things, the first derivative tells you which way you're going. So the slope, as you sort of head up a hill like this, if it's positive, you're heading up the hill. If it's negative, you're heading away down the other side. The second derivative tells you how fast you're getting up that hill. And so that can be used to try to figure out how much to adjust the values by for your next try. And one of the things that you can get out of estimation results is what's known as a gradient or a score function, which is the first derivative with respect to that parameter in the log likelihood function. And you want those to be 0 because what that means is that the slope at the top of the mountain should be 0 if you're really at the top, as opposed to negative or as opposed to positive. So it goes through this process trying to figure out which values make the overall log likelihood the tallest across all the clusters. And when it gets to a point where it's not changing much, it decides it's done. So all stats programs have some sort of built-in criterion that they have to hit to decide when the model is done trying on new values and it's as good as it's going to get. So for instance, in SAS Mix, it looks like this. This is not something you want to mess with. I think the values are chosen for specific reasons, and they probably depend on the estimation problem to be solved. So this is one thing to keep in mind when comparing results across packages. If the convergence criteria is different, then that could be one of the reasons for different results. So once it's decided it's done, it spits out those estimates along with indices of how trustworthy they are, which are leading to the standard error for each parameter. But there's some steps that you have to get here. So because the idea of steepness is embedded in this, the idea that a parameter is really most likely if the mountain is really, really tall and skinny versus like really flat like this. Oh, come back. Flat is bad. Skinny and tall is good. So a tall one would have stronger second derivatives, but that's actually sort of the opposite of precision. So the first thing we do is multiply that by -1, and then we take the inverse. And so then we end up with something like this. The parameter is inversely related to the second derivatives of each of the functions. So we end up with these standard errors that get spit out that are trying to ascertain basically they're trying to tell us like inversely how trustworthy the results are, where smaller standard errors mean the mountain is taller and skinnier as we would like to see. The fixed effects then, here's a formula by which we compute them. I don't need you to memorize this formula or really understand it, but all I want to make is the point here. Once we know V, once we know the values of the random effect variances, covariances, and residual variance at level 1 that create this V matrix, all we then need is the data, the predictors, and the outcomes. Those three pieces of information are what we throw into these equations here to get the actual fixed effect estimates, as well as their sampling variance, which is the idea of standard error squared on the diagonal, and plus the covariances among the standard errors, because in estimation, if one thing goes up, something else may have to come down to compensate. So the point of the story is that adding a lot of predictors with fixed effects to your models aren't going to cause estimation problems because they just get computed. They don't have to get searched for as part of the multidimensional mountain, whereas adding extra random effects does increase the dimensionality of the search process. And I just wanted to show you some corollaries to how this looks in traditional regression as well, where V is replaced, but otherwise it looks somewhat similar in shape. In particular, if we go down to the scalar version here, we have residual variance rather than V. So fixed effects are computed in these models. That stops being the case once we move into generalized models, in which case fixed effects do need to be searched for iteratively along with all of the model for the variance parameters. And then we have Emil versus Remmel. So this process of trying out values that create V until you get to the combination that make everyone's data the tallest works the same way for ML versus Remmel, but they define the likelihood for height in a different way. And this is the most direct way to say it, that ML is the divide by n version of variance, whereas Remmel is the n-1 version that corrects for the number of fixed effects that you needed to figure out before you could get to the predicted value of y. So just one if it's only the mean, 1 plus however many fixed slopes of predictors if you have a more complex model, but it's the same principle of n minus something. So in using ML, the n version means that the variance that you end up with is going to be too small, downwardly biased, by a factor of level 2 n minus k, where k is the number of fixed effects. The scary version of it is this. So ML is the top version here. Remmel looks pretty much identical except for that right here, and then this extra piece. And people way smarter than me figured out, and then I copied from them, to indicate what this thing actually means. And what it translates into is the sampling variance of your fixed effects. So literally like that part is added back in to the log likelihood, because in order to know what variance you have left over, you have to have your fixed effects in the model first. So even though they don't get searched for, they're part of the story, and Remmel takes that into account, whereas ML doesn't. So it's adding back in uncertainty due to the estimation of the fixed effects that happens at the same time. So for this reason, because of this extra piece of the fixed effects here, redefining what height means Remmel log likelihoods are not comparable across models that have different fixed effects. They're on different scales, essentially. So we can only do -2 log likelihood differences or likelihood ratio tests in Remmel when we're talking about what goes into V, not what goes into gamma for the fixed effects. In terms of model fit, we don't spend a lot of attention on this because we really can't. In contrast to other types of models, such as longitudinal models on balanced time, or confirmatory factor analysis or structural equation models where we're focusing on the fit of covariances across variables, we don't have absolute fit really possible. All we can do in multi-level models is relative fit, where it's like, okay, here's the height of the model with these parameters. Did it get taller with these other things added? So we can use -2 log likelihood, and AIC and BIC note that they start with the same thing. So smaller is always better in these summary values. A little bit more about testing variances greater than 0. So another little complicating factor is that when we're doing likelihood ratio tests, we're not technically supposed to use the straight degrees of freedom for the number of added parameters. That's because whenever you add a parameter that has a boundary of 0, like a variance in this case, the null hypothesis of 0 is not going to be in the middle. So what we would want to do is consider the null hypothesis of 0, and then what would happen if it went negative versus what would happen if it went positive. Since it can't go negative, all of that left-hand side is essentially gone. So for that reason, we would, the more technically correctly, in testing the addition of a random intercept variance, we would compare the difference in -2 log likelihood, treat that as a chi-square, but use it with the mixture of when the variance would have went negative, so degrees of freedom 0, and when it was estimated as positive, degrees of freedom 1. Since degrees of freedom 0 creates a chi-square of 0, that's not a thing. Functionally speaking, all you can do is cut the p-value in half. So here's a picture of this issue. I have an article on your reading list that explains it in much more technical detail, and these tiny little pictures are from that article. So the dashed lines here is for chi-square distribution with degree of freedom 1, which is what the naive way of doing a likelihood ratio test for the addition of a variance would be, versus the mixture one. So as you can see, there's very little difference, practically speaking. What it amounts to is if you're testing the addition of a random intercept variance, your critical value for your chi-square should be 2.71 instead of 3.84. If you pass 3.84, then you don't need to worry about this. The only time you should worry about it is if you get a result somewhere in between the two. Then you probably should do it the rightest way, but you'll have to explain it to people. Analogously, if I am adding a random slope variance and the covariance with the intercept, then the dashed line here is for degrees of freedom 2, and the mixture distribution for degrees of freedom 1 and 2 is this line. So again, very little difference right here. What it translates to in practice is the cutoff for alpha of 0.05 if you're adding a variance that can't go negative, and a covariance that could go negative should be 3.14 instead of 5.99. And again, if you pass this by the more conservative criterion, then you would pass it by this and you don't have to worry about it. Here's a table that I borrowed from this textbook, trying to anticipate what the mixture chi-square cutoffs would be via simulation. Here are 3 that I would tend to use in practice in terms of adding 1 random slope versus 2, or just adding a random intercept. So when you are adding 1 random effect, you can cut your p-value in half. When you're adding 2, then it's a degree of freedom mixture of 1 and 2. After that, it gets tricky because you have to assume that the variances are arrived at independently, which is not going to be the case. So either you go to the trouble to do the mixture chi-square properly, or do some sort of simulation in more complex cases to figure out what it should be, or you just acknowledge that you're being a little bit conservative. That's what I do. In practice, I don't usually care about this unless I'm doing some kind of quant methods research study where it's a simulation and I need to be exact. So in my textbook, for instance, on longitudinal data, I use this tilde squiggle thing to indicate, yeah, it's approximately 2. I'm treating it as 2, even though technically it should be a mixture of 1 and 2. So a little bit about the use. So all software packages that do multi-level models will spit out the use if you want them to, but you don't. Here's why. There are potentially 3 different ways of quantifying differences across clusters in intercepts and in slopes. One is to do a per cluster regression, so ordinary least squares per cluster, figure out the cluster specific intercept and slope, save them, and compute their variance. Another way would be to ask the software to spit out the U values into a data set, and That's the third one here, and then we can compute their variance, or we could estimate the variance of the u's directly in the model, and that's what we're doing in multi-level models. In terms of what's going to happen, there is a well-known result here. The intercept and slopes from individual cluster-specific regressions is going to be biggest, followed by the variance from the model, followed by the variance of the outputted u's, shrinkage. So these u values, another way to say it is that they're factor scores. Here's the messy formula to get them. Here's a little bit more detail about that. The big picture is that the u's that you get out, if you predict them, ask for the software to figure out what they are going to be shrunken. So u's for clusters that look really extreme, or u's for clusters that have smaller numbers of people contributing to them, are going to get pushed to look more like the fixed effects rather than what their cluster-specific intercepts and slopes would be. So they're a weighted function where if the signal from the random effects is stronger, then the higher the weight of the individual cluster-specific intercepts and slopes, whereas if the residual variance is stronger, then there's less weight given to those. So then every cluster's intercepts and slopes would look more the same. So point of the story, u values can be outputted, but you don't need them. They're going to be shrunken. We don't want to treat them as if they're perfectly reliable, because what we wouldn't have is all the error around these regression lines. They're not part of the output if you just ask for u's. So we don't need to output them. We can do analyses where u variance, random intercept and slope variance, is predicted directly in the model, or we can turn those things into predictors of other things in a multivariate setting, such as multi-level SEM. All right, so the grand finale then. Random effect variances and covariances break models. When there's estimation problem, that is why. If you see the words non-positive definite, it means your model is broken and you should not keep it. And ML and REML are both ways of figuring out what parameters make the data the tallest. You can only compare log likelihood values or their AIC and BIC analogs in REML for models that contain the same fixed effects, because only then will they be on the same scale. Ta-da! Thanks for listening. I hope this was helpful and not too terrible, and I hope to see everyone next week.